Now we understood the behavior of pure resistor, pure inductor and pure capacitors when they are excited individually by an alternating voltage source. Now we are ready to understand the phasor diagram of RLC circuit combination. So before going to study the circuit developed with the combination of three elements, let us study the combination of two elements. Now before going to the phasor diagram construction for RLC series circuit, let us draw the phasor diagram of the series circuit containing two elements. So let us start with the RL circuit. So if we have a RL circuit, then what will be the phasor representation? So let us draw one RL circuit containing two elements, that is pure R, pure resistance R and pure inductance L, without any capacitive component in this circuit. So if we draw the circuit, we will understand that the circuit will drive, that is voltage will give some current will be conducted through the R and L, and those currents will be same current because they are connected in series. So we can tell that this current will be flowing in this direction, and that will be equal to I, equal to IR, equal to IL. Now voltage across the resistance will be denoted by VR, say, and voltage across inductor will be VL. Let us suppose these two voltages will be the voltage drop across these two elements. Now if we want to draw the phasor representation of the voltage across R, voltage across L and the current, then we have to take the reference vector first, and as per the convention for series circuit phasor diagram procedure, so we will take the current as the reference. So I equal to IR equal to IL. Now we know that the phasor for the resistor voltage drop, that is the voltage drop across resistor VR, will be in the same phase. So we will draw the voltage across R, that is VR. So in this situation we will consider that the reference is IR because we are going to draw the resistance drop. So the drop across the resistor. So here we have to consider the current through the resistor and voltage across resistor. So now as the series circuit is this, so automatically I is equal to IR equal to IL. So whenever we will draw the voltage drop across any element, so we have to take this current as the current through that element. So that's why I am mentioning that let us consider this phasor is IR, and accordingly the VR will be in same phase. Now if we are going for drawing the phasor for the voltage drop across L, so we will consider this current as IL, and accordingly we have to draw one phasor perpendicular to this current, that is IL, and which will be located after 120 degree rotation in the anti-clockwise direction, because we know by convention that voltage across inductor leads over the current passing through the inductor. So we will get the phasor VL after pi by 2 rotation in the direction of anti-clockwise direction. So if we think about the phase angle of the entire circuit, so we have to sum up these two phasors and we will get one voltage, resultant voltage, which will be say VT, we can consider that. So that is total voltage. So VT will be the total voltage here, total voltage drop, and this will be the phase angle. So VT and I, that will be the phase angle. Say consider this phi. Now this phi will depend on two parameters, that is R and XL, that is omega L. So these two parameters will tell that phi will be how much. So here we have to understand that the resistor, if resistor is very big, then resistor will try to bring that phasor in this direction, and if inductor is big or the frequency is big, that is if the omega is big, then this inductive component will try to bring that phasor in this direction. So accordingly the phasor will move or shifted either in direction, this direction. So phase angle will be lesser and lesser if the resistor component or the resistive component increases, or if the inductive reactance increases, then the phasor will move towards the perpendicular direction, and it will become 90 degree if resistive element is 0, as we have studied in the earlier section. So similarly, if we go for the capacitive circuit with resistor, then we will be able to construct one circuit, that is RC circuit. Now if we want to draw the phasor diagram for RC circuit, we have to draw the circuit diagram first, that is R and C, which will be excited by one voltage supply, and then we will be checking whether and then we will be denoting the voltage drop across R as VR and voltage drop across C is VC, and current will be passing through all these elements as I equal to IR equal to IC, and total voltage will be VT here also. So total voltage will be VT, resultant voltage. So let us see what will be the phasor diagram. So as per convention of the series circuit, we will draw I equal to IR equal to IC, and by convention voltage drop across the resistor, that is VR, will be in same phase, and VC will be in perpendicular to this current, but it will be lagging. So in case of capacitor, current leads over the voltage, so the voltage drop across the capacitor will be denoted by a lagging vector, that is VC. So this will be obtained by rotating of pi by 2 in clockwise direction by the convention. So now if we want to draw the resultant of these two, so we will find one phasor in this direction, and the angle between these two, that is current, and the VT, that is resultant, will be the phase angle. Now in this case also, the resistor, if it is a big value, then resistor will try to bring the resultant in its direction, in the direction of current, and if the 1 by omega c increases, then it will be going in the perpendicular direction. So whenever resistor in the circuit will be 0, so it will be exactly located along the 90 degree angle with the current. So whatever we have studied in the earlier section. So here also the phase angle depends on, say, XC, that is capacitive reactance 1 by omega c, and R. So depending on these two values, phi will be decided, that it will be how much. So this circuit will be having some voltage, resultant voltage, which will lag behind the current for the RC circuit, and for the RL circuit the voltage, resultant voltage, will be obtained as a leading voltage over the current. So here this omega L is called the magnitude of inductive reactance, that is XL, and here the 1 by omega c is known as the capacitive reactance, and this is the amplitude of the capacitive reactance XC.